Welcome to Dark Sky Dive, where we explore the engineering marvels orbiting high above our blue planet at incredible speeds today. Over 400 kilometers above us, a massive structure races through the void at nearly 28,000 kilometers every single hour. It is not a simple spaceship, nor is it a lonely satellite drifting aimlessly in the cold, dark expanse of space. This is the International Space Station, the single largest structure ever constructed by human hands within the vacuum of outer space. However, few people realize that this orbital giant was not built in space from the beginning of its long journey. It was born inside advanced factories on Earth, manufactured piece by piece before ever touching the stars above our heads. Each individual part, known as a module, is actually a completely independent flying house designed to sustain human life in space. We must ask ourselves, why is it impossible to build the entire space station as one solid block from the start? There are no construction cranes in orbit, and there are currently no factories capable of manufacturing heavy structures in space. Everything must be manufactured on Earth, launched by powerful rockets and then assembled manually in a weightless environment by astronauts. This reality forces engineers to design the station in modules, where every block performs a vital function for survival. If we consider the space station a city, then each module is a building launched into the sky and connected. Let us step inside the factory. Each module is crafted in a giant clean room where the environment is strictly controlled. The air is continuously filtered because even dust, smaller than bacteria, must be eliminated to prevent future failures in space. Temperature and humidity are monitored with absolute precision, ensuring that the materials remain stable during the entire construction process. The framework is typically made from aluminum alloys, materials chosen because they are incredibly light, yet exceptionally durable under stress. These walls must withstand immense internal pressure and the extreme temperature differences found in the harsh environment of outer space. A typical module is several meters long and weighs tons, yet it must be accurate to the very single millimeter. Because out there in the void, there is absolutely no room for error, and mistakes can lead to fatal consequences. What makes a space station module special is that it is much more than just a hollow metal tube floating. Every module contains vital life support systems that generate oxygen, regulate pressure, and filter out dangerous carbon dioxide for astronauts. They are packed with electrical power systems, thermal controls, and advanced computers that monitor every aspect of the module's health. If necessary, astronauts can live independently within a single module for extended periods, relying on its backup emergency systems. That is the reason why engineers often refer to these incredible feats of engineering as their flying houses in space. Before launch, the module must pass a series of torture tests on Earth that are harsher than space itself. Pressure tests involve repeated compression and release cycles to simulate the vacuum environment and ensure the seals hold tight. Vibration testing simulates the violent shaking forces that occur when the powerful rocket engines ignite and lift off the ground. Thermal tests expose the structure to temperatures ranging from minus 150 to plus 120 degrees Celsius. Emergency simulations test how the systems respond to catastrophic events like fire, toxic gas leaks, or sudden loss of power. Only if the module survives all these brutal tests is it considered qualified to travel to the final frontier. When the module is finally loaded onto the rocket, it marks a moment of no return for the engineering team. In just the first few minutes of flight, the acceleration increases to many times the force of Earth's natural gravity. Intense shaking could destroy the structure if there is even the smallest manufacturing error hidden within the metal frame. Temperature and atmospheric pressure change abruptly as the vehicle punches through the atmosphere and enters the vacuum of space. Historically, most major space station modules were carried into orbit by the space shuttle or modern heavy-lift rockets. A single failed launch means billions of dollars and years of hard work vanish in a matter of seconds. Once the module reaches stable orbit, the hardest part of the construction process is actually just beginning for the crew. Astronauts or robotic arms must locate the free-floating module and position it with extreme care for the connection. They must align the connecting ports with absolute precision, ensuring the locking mechanisms are perfectly centered before making contact. The module is then mated to the station using mechanical locks, a process that requires patience and steady hands. A misalignment of just a few centimeters could cause the entire docking process to fail or damage the ports. There are no hammers here, and no natural gravity to help. Every action takes place in absolute zero gravity. Even when the module is physically attached, it cannot be used immediately. It is merely a cold, dark shell. Astronauts must manually connect power lines, data cables, and air ducts to integrate the new room with the station. They establish vital data connections and air circulation systems, bringing the dormant module to life for the very first time. They meticulously check for pressure leaks, because a bad seal is a silent killer in the vacuum of space. Just a small error could cause the entire module to be sealed off forever to protect the rest of the station. This is why every single procedure is practiced hundreds of times in underwater pools on Earth before the mission. No single nation can build a modern space station alone. It is a testament to global cooperation and engineering. The ISS is the result of collaboration between NASA, Roscosmos, the European Space Agency, and the Japan Aerospace Exploration Agency. Each module reflects the engineering philosophy of its nation, yet, when connected, they form a unified home beyond Earth. The space station is never truly finished. It is a dynamic structure that changes and evolves over the decades. Modules are added, upgraded, replaced, or even removed, much like a living city that grows and adapts over time. Each new generation of modules allows humans to stay longer in space and understand our bodies in zero gravity. They help us prepare for future missions to the Moon and Mars, serving as a stepping stone for exploration. Why do we build these flying houses? Because to go further, we must first learn how to live apart from Earth. Each module is an experiment, a laboratory, and a silent declaration that humans are not bound to the ground. We are learning to carry life with us into the cosmos, building a future among the stars, one module at a time. From the factories on Earth to the silence of orbit, this journey represents the pinnacle of human ingenuity and determination. Behind every floating module are thousands of dedicated minds on Earth working together to make the impossible a reality. As technology advances, the next generation of space modules will be larger, safer, and more capable than ever before. New materials are being developed that will make future stations lighter to launch, yet stronger against cosmic radiation. We are even exploring inflatable habitats that launch small but expand to provide massive living quarters for deep space crews. Automation will play a larger role, with robots potentially assembling structures far away from Earth before humans arrive. The lessons learned here are directly applied to the Lunar Gateway, our next outpost orbiting the Moon very soon. Docking procedures perfected in low Earth orbit will ensure the safety of astronauts traveling deeper into the solar system. Commercial companies are now entering the arena, planning their own private stations to manufacture goods and host tourists. Factories in orbit could soon produce unique materials like perfect optical fibers that are impossible to make under gravity. Microgravity also offers a unique environment for printing human tissues and organs, revolutionizing medicine for patients back on Earth. But let us look back at the Earth one more time. It reminds us of the fragility of our existence. Living in these modules requires strict discipline. Exercise is mandatory to prevent muscle atrophy and bone density loss. Even simple acts like drinking water or sleeping become complex engineering challenges that the module design must solve. The water recovery system recycles almost all liquids, turning waste into pure drinking water, closing the loop completely. Waste management is equally critical. Trash is compacted and loaded into cargo ships to burn up upon re-entry. Regular cargo missions from Earth bring fresh food, new experiments, and replacement parts to keep the station operational. These deliveries are the lifeline connecting the crew to their home, bringing essential supplies and reminders of their families. The view from these modules is unlike anything else. The aurora borealis dances beneath them in waves of green light. They watch giant storms swirl over the oceans, observing the planet's weather patterns to help scientists understand climate change. They witness 16 sunrises and sunsets every single day, a rapid cycle of light and dark that never ends. This rapid cycle forces them to adhere to a strict schedule based on universal coordinated time to maintain sanity. Danger is always present. Space debris traveling at bullet speeds can threaten to puncture the module walls at any time. The station must occasionally fire its thrusters to maneuver out of the path of dangerous tracking debris objects. Shielding layers called Whipple shields protect the modules by breaking up small impactors before they can penetrate the pressure hull. Layers of Kevlar and ceramic fabrics are used to absorb the kinetic energy of particles hitting at hypersonic speeds. Space inside is a premium commodity. Every square inch of the walls, ceiling, and floor is utilized for equipment. Even the toilet is a complex machine that requires regular maintenance to function correctly in the absence of gravity. Tools must be tethered or velcroed down, or they will drift away and become lost or dangerous projectiles. Haircuts are done with clippers attached to a vacuum cleaner, preventing stray hairs from clogging air filters or equipment. Meals are a communal time. Food is often dehydrated and must be rehydrated with water before it can be eaten. Salt and pepper are available in liquid form, as powders would simply float away and irritate eyes or lungs. Communication technology allows them to video chat with family, bridging the massive distance that separates them from their loved ones. The first module, Zarya, was launched in 1998, marking the beginning of this incredible era of construction. It was soon followed by Unity, the first American component, connecting two former rivals in a joint, peaceful mission. Over the years, the station grew larger and more complex, evolving into the massive orbital laboratory we see today. The massive truss structure was added to support giant solar arrays, providing the immense power needed for scientific research. Maintenance is constant. Astronauts regularly perform spacewalks to upgrade batteries and replace aging components on the station's exterior. A spacewalk is the most dangerous activity, exposing humans to the vacuum with only a suit for protection. They rely on a thin steel tether to keep them attached to the station, preventing them from drifting away forever. The gold visor protects their eyes from the blinding sun, which is significantly brighter than anything experienced on Earth. Inside, the crew coordinates their daily tasks with mission control centers located in Houston, Moscow, Tsukuba, and Munich. Hundreds of personnel on the ground work around the clock to support the few people living in space. The experiments conducted here have led to breakthroughs in medicine, materials science, and our understanding of the universe. Protein crystals grown in microgravity help researchers design better drugs for treating diseases like cancer and muscular dystrophy. Combustion experiments reveal how fire behaves differently in space, helping to improve fire safety on Earth and in space. Robotics testing paves the way for future missions where machines will assist humans in building infrastructure on other planets. But beyond science, the station serves as a symbol of what humanity can achieve when we work together. It inspires the next generation of engineers, scientists, and dreamers who look up and see a moving star. One day, this station will reach the end of its life and be guided safely into the ocean. But its legacy will live on in the private stations and deep space outposts that will follow in its wake. The lessons learned from building and maintaining these modules are the keys to unlocking our future on Mars. New rockets will soon carry larger modules, allowing us to build structures that dwarf the current space station. We may even see rotating stations that create artificial gravity, solving the health problems associated with long-term weightlessness. The knowledge gained from the ISS is already being taught to students who will design the spacecraft of tomorrow. From hand-drawn blueprints to digital twins, the evolution of space engineering has been rapid and absolutely relentless. We have learned that every bolt, every seal, and every line of code matters when lives are at stake. We have learned patience, resilience, and the ability to solve problems that no one has ever encountered before. The International Space Station stands as a beacon of civilization, a shining example of what peace and science can achieve. It also gives us a unique perspective on our own planet, highlighting the need to protect our only home. Astronauts often return with a shifted perspective, realizing that borders are invisible and we are all one crew. The journey from raw aluminum in a factory to a life-sustaining habitat in orbit is a modern miracle. It is a journey made possible by the unseen hands of thousands who will never leave the ground themselves. As we speak, new modules are being built, tested, and prepared for the next chapter of human space exploration. The rockets are getting bigger, the technology is getting smarter, and our ambitions are reaching further than ever before. We build these flying houses not just to survive, but to thrive and learn in the great unknown. The universe is vast and dangerous, but our engineering has carved out a small, safe island amongst the stars. So the next time you see a bright light moving across the night sky, remember what it really is. Remember the clean rooms, the vibration tables, the rocket fire, and the steady hands that put it together. It is not just a machine. It is a home, built by humans, for humans, against all the odds. The story of the space station is far from over. In fact, we are just finishing the first chapter. We are preparing to leave low Earth orbit and take our modular homes to destinations we have only dreamed of. The cosmos awaits us, and thanks to these engineering marvels, we are finally ready to answer its call. We salute the visionaries and the builders who turned science fiction into reality, one module at a time. This has been the incredible story of how we build our homes in the sky, defying gravity and nature. Thank you for joining us on this journey through the factory floors and into the vacuum of space today. This is Dark Sky Dive, signing off. Subscribe for more deep dives into the technology that powers our future.